Hi students, welcome to the 8th lecture in Permutations and Combinations. I hope you have watched the first 7 lectures. So in this lecture we are going to deal with circular permutations including all the problems in 5C. Okay, before going into details of this lecture, let me recall what we have done in the first 7 lectures. So in the first 7 lectures we have discussed about fundamental principle of counting, both multiplication and addition. So coming to multiplication, if a task can be divided into two works, W1 and W2, and the number of ways of doing W1 is M and number of ways of doing W2 is N, and the total number of ways of completing the task is equal to number of ways of doing W1 times number of ways of doing W2, which is equal to M times N. Next, coming to addition, if a task can be performed in two formats, W1 or W2, then the number of ways of completing the task is equal to number of ways of completing W1 plus number of ways of completing W2. So here you have to understand, you have to remember these two things. Whenever N comes, you will have multiplication. Whenever R comes, you have addition. So these are the two things that you have to remember throughout this chapter. And then we have defined factorials. So by this time I think you are familiar with factorials now. And then we have defined linear permutations and circular permutations. We have discussed a few differences between these two. Anyway, we are going to deal with circular permutations in detail in this lecture. We are going to count how many circular permutations are there in this lecture. In the previous lectures, we have counted number of linear permutations. Number of linear permutations of n distinct objects taken R at a time is denoted by NPR, and the expansion of NPR is n times n minus 1 times n minus 2, so on up to n minus R plus 1, or else we can write it in the form of n factorial upon n minus R factorial. So I repeat, NPR is equal to n factorial upon n minus R factorial, where NPR stands for number of permutations of n distinct objects taken R at a time. Okay. So by convention we define NP not to be equal to 1, and NPN turns out to be n factorial. And we have seen few results related to NPR. NPR is equal to n times n minus 1 p R minus 1, or else you can just write it as n times n minus 1 times n minus 2 p R minus 2. We have given different proofs for this one using the formula and the one using combinatorial argument. And the next one, NPR is equal to n minus 1 PR plus R times n minus 1 PR minus 1. So here R times n minus 1 PR minus 1 stands for number of permutations of n distinct objects taken R at a time, which always contain a particular object. And here NPR stands for number of permutations of n distinct objects taken R at a time. And n minus 1 PR stands for number of permutations of n distinct objects taken R at a time without including a particular object. Therefore, the total number of permutations is equal to number of permutations without including a particular object plus number of permutations which always include a particular object. So this is the proof for this one, or else you can use the formulas to prove this one. And then we have these results. The sum of all R-digit numbers using the digits, using n digits which does not contain 0 is equal to n minus 1 p R minus 1 times sum of the given digits times 1111 R times. The sum of all R digit numbers that can be formed using the given n digits in which 0 is not there is equal to n minus 1 p R minus 1 times sum of the given digits times 11111 R times. Next, what happens if 0 is there? If 0 is there, we have this formula. N minus 1 p R minus 1 times sum of the given digits times 1111 R times minus n minus 2 p R minus 2 times sum of the given digits times 11111 R minus 1 times. So why we are deleting this one? This term is all R digit numbers which start with 0 is same as saying R minus 1 digit numbers. I repeat, r digit number starting with r same as r minus 1 digit numbers. So we are indirectly counting these extra terms. So we have to remove these extra terms whenever 0 is there. So whenever 0 is there in the given digits, you have to be little bit careful. Depending upon the digits, we will use the first formula or we will use the second formula. We will use first formula if 0 is not there in the given digits. We will use the second formula if 0 is there in the given digits. Next, the number of injections from a set A with m elements into a set P with n elements is npm, as long as m is less than or equal to n. Or if m is greater than n, then the number of injections is going to be 0. Next, we have this formula related to derangements. Whenever you have a problem related to derangements, you have to use this formula. Anyway, if time permits, we can give the proof of this formula. The proof of this formula is not given in the textbook. We can give the proof of this formula using principle of inclusion and exclusion. So if time permits, I will deal with principle of inclusion and exclusion in the last lecture. Okay. Anyway, the formula of derangement is n factorial times 1 upon 2 factorial minus 1 upon 3 factorial plus 1 upon 4 factorial and so on up to minus 1 whole to the power of n times 1 upon n factorial. And we have discussed about specific order and the number of permutations of n distinct objects on which specific order is imposed on k objects is n factorial upon k factorial. So if specific order is imposed on k objects, then the number of permutations is going to be n factorial upon k factorial. And then in the last lecture we have dealt with permutations when repetitions are allowed. So when repetitions are allowed, the number of permutations is going to be n raised to r. When repetitions are not allowed, then the number of permutations is going to be npr. So this stands for number of permutations of n distinct objects taken r at a time when repetitions are not allowed. When repetitions are allowed, we have this formula n raised to r. So one more thing you have to look into consideration is in this npr, r is always less than or equal to n. When repetitions are not allowed. When repetitions are not allowed, r should be less than or equal to n. When repetitions are allowed, there is no restriction on r. No restriction on r when repetitions are allowed. So this is one more difference that you have to remember. When repetitions are not allowed, r should be less than or equal to n. When repetitions are allowed, there is no restriction on r. R can be less than or equal to n, or r can be greater than n also. So n raised to r gives the number of permutations of n distinct objects when repetitions are allowed. When repetitions are not allowed, then the number of permutations are going to be npr. Next, the number of permutations of n objects with at least one repetition is n raised to r minus npr. Because n raised to r gives the total number of permutations and npr gives the total number of permutations in which repetitions are not allowed. Number of permutations with at least one repetition is equal to total permutations minus number of permutations without repetitions. Total permutations is n raised to r, permutations without repetitions is npr. Therefore, permutations with at least one repetition is going to be n raised to r minus npr. Next, we have looked into the definition of palindrome. A number or a word when read from left to right or from sorry. A number or a word is said to be a palindrome if it reads the same from left to right or from right to left. And we have given a few examples. ATTA, ROTOR, 1 2 1 2 1 and so on. Okay. So number of palindromes of length r is given by these two formulas. N raised to r upon 2 when r is even n raised to r plus 1 upon 2 when r is odd. So the number of palindromes of length r formed using the given n objects is going to be n raised to r upon 2 when r is even, n raised to r plus 1 upon 2 when r is odd. Next, while doing few problems, we have derived these two results. Then the number of bijections, number of functions from a set A with m elements into a set B with n elements is going to be n raised to m. I repeat, the number of functions from a set A with m elements into a set B with n elements is going to be n raised to m. So if you are getting confused here, it is good to remember like this: cardinality of B raised to cardinality of n. Cardinality of A. Cardinality of B raised to cardinality of A. And the number of surjections from a set A with n elements into a set B with 2 elements is going to be 2 raised to n minus 2. So these are the two results that we have seen while doing few problems related to permutations with repetitions. Now let us look into circular permutations in detail. Anyway, the definition of circular permutation is like this. We have discussed this definition in the first lecture itself. Anyway, it is just a recall of the first lecture. From a finite set of similar or dissimilar things, selecting a few or all of them and arranging them in a circle is called as a circular permutation. So if you arrange things in a line, it is called as a linear permutation. If you arrange things on a circle, then it is going to be a circular permutation. So example, we have this one: A, B, C, D. So this is a circular permutation, whereas this one A, B, C, D is going to be this is a linear permutation, whereas this one is going to be a circular permutation. Anyway, we have studied the differences between linear permutations and circular permutation. So let me recall those differences quickly. So in a linear permutation, we have the notion of first place, second place, and last place. But whereas in a circular permutation, we don't have the notion of first place, second place, and so on. And few linear permutations result in a single circular permutation. Anyway, so here in this linear permutation, I can say that B is in the second place. But here in this circular permutation, I cannot say that B is in the second place. So in a circular permutation, I can specify the position of an object with reference to another object. So here I can say that B is in the clockwise direction of A, or D is in the anti-clockwise direction of A. But here in a linear permutation, I can directly specify the position of B without referring to other objects. So here I can say that B is in the second position. But here, if I want to specify the position of B, I can specify the position of B with respect to another element. I can say that B is to the clockwise direction of A, or B is in the anti-clockwise direction of C. Okay. So I can read this permutation as ABCD. If you read this permutation in clockwise direction, then you'll have ABCD. Now let me draw another permutation. This is A, B, C, and D. So if you read this permutation in clockwise direction, you will have ABCD. If you read this permutation in anti-clockwise direction, then you will have this ABCD. Okay. If you read this permutation in clockwise direction, then you will have ADCB. So you can take these two permutations as two different permutations. Two different permutations. Even though if I read this permutation in clockwise direction, I will get ABCD. If I read this permutation in anti-clockwise direction, I will get ABCD. But these two permutations will be treated as two different permutations. Anyway, there are few cases where clockwise permutation and anti-clockwise permutation will be treated as a single permutation. We will look into those cases later. But this is the story of circular permutations precisely. Now, anyway, as I mentioned earlier, the main motto of this chapter is to count the number of permutations and number of combinations. So here the next goal is to count the number of circular permutations. Now, this theorem tells us how many circular permutations we can form using n distinct objects. And the statement of the theorem is like this. The number of circular permutations of n dissimilar things taken all at a time is going to be n minus 1 factorial. I repeat, the number of circular permutations of n distinct objects taken all at a time is going to be n minus 1 factorial. So we have to give the proof for this statement. So let the given objects be A1, A2, A3 and so on up to AN. These are our n objects. Now we have to count how many circular permutations we can have. Let the number of circular permutations be capital M. Now we have to find out what is this capital M stands for, or what is the number of circular permutations. Let me write one circular permutation for you, A1, A2, A3 and so on up to AN. This is one circular permutation. This one circular permutation gives rise to n linear permutations, A1, A2, A3 and so on up to AN, A2, A3, A4 and so on up to AN, A1, A3, A4 so on up to AN, A1, A2 and so on AN, A1, A2 and so on up to AN minus 1. So this one circular permutation gives rise to n linear permutations. So if I read this circular permutation starting from A1, I will get the first one. If I read this circular permutation starting from A2, I will get the second one. If I read it from A3, then I will get the third. If I read it from AN, I will get the last one. So one circular permutation gives rise to n linear permutations. Now let me write a statement for you. One circular permutation gives rise to n linear permutations. Now total I have m circular permutations, but the total number of linear permutations is going to be n factorial. Okay. Now let me explain this for you. I have to find out this m. Now one circular permutation gives me n linear permutations. Now I have to find out how many circular permutations gives rise to n factorial linear permutations. Okay, if the cost of one pen is equal to n rupees, I have spent n factorial rupees. Now how many pens I have bought? I repeat, if the cost of one pen is equal to n rupees and I have spent n factorial rupees, now I have to find out how many pens I have bought. So this implies 1 is to n is equal to m is to n factorial. So this gives me m is equal to n factorial upon n, which is equal to n minus 1 factorial. So this is my total number of circular permutations formed using n distinct objects. Or else you can give a second proof for this one. So the given objects are A1, A2 and so on up to AN. This is my second proof. So I have to arrange these n objects on a circle. So let me draw a circle. On this circle I have 1, 2, 3 and so on up to n positions. So since it is a circle, I cannot say that this is my first position, this is my second position and so on. Okay, I can fill A1 in any of these n positions. I can fill A1 in any of these n positions. But A1 can be filled in any of these n positions in only one way. A1 can be filled in any of these n positions in only one way, because all these positions are identical. If I draw this one, 1, 2, 3 and so on up to n linear positions. A1 can be filled in these n linear positions in n ways, but A1 can be filled in n circular positions in only one way, because there is no starting position and there is no ending position. Here we have the notion of starting and ending. If A1 is placed here, then I can say that A1 is in the starting position. If A1 is placed here, then I can say that A1 is in the second position. If A1 is placed here, then I can say that A1 is in the last position. But if A1 is here, I can still say that A1 is in the first position. If A1 is here, then I can still say that A1 is in the first position. If A1 is here, then I can still say that A1 is in the first position. Now, I can fill A1 in any of these places in only one way. A1 can be filled in only one way. Filled in only one way. After filling A1 in any of these n positions, now how many positions I have? So I have occupied only one position, so the number of positions that are left is going to be n minus 1, and the number of objects that are going to be left is n minus 1 objects. Now I can fill these n minus 1 objects in these n minus 1 places in n minus 1 factorial ways. After filling A1, we have n minus 1 objects and n minus 1 places. Therefore, the number of ways of filling these n minus 1 places using these n minus 1 objects is going to be n minus 1 factorial. One times n minus 1 factorial, which is equal to n minus 1 factorial. These are our total number of circular permutations formed using the objects A1 to An, or number of circular permutations of n objects taken all at a time is equal to n minus 1 factorial. Now in these circular permutations we have an exception. The exception is hanging type of circular permutations. Okay. In case of hanging type of circular permutations like garland of flowers or chain of beads, the total, clockwise and anti-clockwise permutations both are treated as a single permutation. Since we are treating two permutations as a single permutation, the number of permutations is going to be n minus 1 factorial upon 2. So the number of circular permutations of n distinct objects is going to be n minus 1 factorial, but the number of circular permutations of n objects, when the objects are garland, when the objects are flowers or beads, the number of permutations is going to be n minus 1 factorial upon 2. So why we have this n minus 1 factorial upon 2, we will see, or why we are treating clockwise and anti-clockwise as a single permutation, we will see. Okay. So let us consider this example. So here we have three people, A, B and C. So this person is A, B and C. We have three people, A, B and C. So assume that these three people are sitting on a table, round table. So we have this round table and we have this B, A and C. C is to the clockwise direction of B and A is to the anti-clockwise direction of B. in this permutation. Or else here if you see the picture, A is sitting on the right hand side of B and C is sitting on the left hand side of B. Okay, if I want A to sit on the left hand side and C to sit on the right hand side, then what I have to do is I have to interchange these two. I can interchange these two only by making them stand. So these two people have to stand up and they have to swap their positions and then they have to sit. Then only I will have this permutation B, A and C. If these two people swap their positions, then I will have this position B, A and C. So here I have B, C and A. Starting from B, here I have B, C and A. Starting from B, here what I have is B, A and C. So these two permutations are different. Okay. Now let us come to this one. So here we have 3 beads. So the middle one is white. It is little bit gold in color. So let me denote it by G. This is little bit pinkish in color. So let me denote it by P. So we have this circular permutation. So here we have W, here we have G and here we have P. If I wear this chain, then what happens is this gold color bead will come onto the chest. This gold color bead will come onto the side where the heart is located. Now this pink color will go to the right side. This white color will be to the bottom or will be in the middle. So what you have to observe here is the gold color bead will come onto the chest side. Okay. Now I don't want this gold color bead coming onto my chest side. I want this pink color bead to come onto my chest side. And what I can do is I can rotate this chain. And then I can wear it. If I rotate this chain, so after rotation what I will have is, here I will have white as it is, and here I will have pink, and here I will have gold. So without removing these beads, removing these beads from the chain, I can rotate this chain and then I can wear it. If I rotate this chain and I wear it, this will be the arrangement. Without rotation, this will be the arrangement. So without removing these beads from the chain, I can get these two arrangements. For these two arrangements, we have a single chain. If I want to wear it like this or if I want to wear it like this, we have to pick only one chain. So whether you can wear it clockwise direction or whether you can wear it anti-clockwise direction is up to you. So if I wear it as it is, I will have this one. If I rotate this chain and wear it, then I will have this arrangement. So these two arrangements results from a single chain. So here clockwise and anti-clockwise arrangements are treated as a single arrangement in case of chain of beads or garland of flowers. Okay. So whereas here these two permutations will be treated as two different permutations. So only in these exceptions we have this n minus 1 factorial upon 2. With this we have completed the concepts related to circular permutations. Now we have to solve few problems. And the first example problem is like this. In how many ways we can arrange 5 boys and 5 girls around a circle? So here we have 5 boys and 5 girls. So total 10 people. So in how many ways we can arrange these 10 people around a table? That is our question. So number of circular permutations of n objects is equal to This is equal to n minus 1 factorial. So here n is equal to 10. Therefore, number of arrangements is equal to 10 minus 1 factorial. So in 9 factorial ways you can arrange 5 boys and 5 girls around a circle. So if you want to arrange these 5 boys and 5 girls in a straight line, then the answer is going to be 10 factorial. But if you want to arrange these 5 boys and 5 girls around a circle, then the answer is going to be 9 factorial. It is not going to be 10 factorial, it is going to be 9 factorial. The next problem is like this. Find the number of ways of arranging 8 people around a circle if 2 people wants to sit together. So we have 8 people, we have to arrange these 8 people around a circle. So out of these 8 people, there are 2 particular people, those 2 people wants to sit together. So whenever you have this term sitting together or coming together, what you have to do is you have to tie up those objects who are supposed to come together. We have 8 people, 2 wants to sit together. So what you can do is you can tie up these 2. Now we have 7 units. In general we have 8 people, but here we have only 7 units of people. So in these 7 units we have 6 individual and 1 unit consisting of 2 people. Now in how many ways we can arrange these 7 units around a circle? Now these 7 units can be arranged in (7 minus 1 factorial), that is 6 factorial ways. But this 1 unit consisting of 2 people can be arranged in, we have 1 unit consisting of 2 people. These 2 people can be arranged in 2 factorial ways. Therefore, total number of arrangements is equal to 6 factorial times 2 factorial. So the number of ways of arranging these 7 units is equal to 6 factorial. But in this 1 unit consisting of 2 people, I can arrange these 2 people among themselves in 2 factorial ways. Therefore, the total number of arrangements is going to be 6 factorial times 2 factorial. Next, we have few example problems to understand the concepts. The first example problem is like this. Find the number of ways of arranging 5 boys and 5 girls around a circle. So let us try to answer this one. So we have 5 boys and we have 5 girls. So total we have 10 people. So in how many ways we can arrange these 10 people around a circle? So number of ways of arranging is equal to is equal to 10 minus 1 factorial, because the formula for the number of circular permutations is going to be n minus 1 factorial. The number of circular permutations of n objects is n minus 1 factorial. The number of circular arrangements of these 10 people is going to be 10 minus 1 factorial. So if you want, you can write it as 9 factorial. Okay. So let us answer the second question. Find the number of ways of arranging 8 people around a table in which 2 particular people wants to sit together. I repeat the question. Find the number of ways of arranging 8 people around a table in which 2 particular people wants to sit together. So we have seen these kind of problems in linear permutations. Now we have the same kind of problems in circular permutations. So here we have 8 people. in which 2 wants to sit together. So what you can do is we can tie up these 2 people. Tie up these 2. Now if you tie up these 2, then what we can have is we have 7 units. So if we have these 7 units of people. Now we can arrange these 7 units in now we can arrange these 7 units in 7 minus 1 factorial ways. But in this one unit consisting of 2 people, I can arrange them among themselves in 2 factorial ways. In that special unit, we can arrange them in 2 factorial ways. Therefore, the total is equal to 7 factorial times 2 factorial. Sorry, 6 factorial times 2 factorial. 7 minus 1 factorial times 2 factorial, which is equal to 6 factorial times 2 factorial. So whenever we have a problem like coming together, we can tie up those things. So after tying up, we can treat them as one unit. In that one unit, we can arrange themselves in 2 factorial or 3 factorial depending upon the number of people. Okay. Now let us move on to the next question. Find the number of ways of arranging 8 men and 4 women around a table. In how many of these arrangements all women come together, no 2 women come together? So let us write down the information we have. We have 8 men and 4 women. So total we have 12 people. So number of ways of arranging these 12 people around a table is equal to 12 minus 1 factorial. Number of ways of arranging these 12 is equal to 12 minus 1 factorial, which is equal to 11 factorial. Now let us answer the first one. All women come together. All women come together means if you tie up all women implies we have 8 plus 1, which is equal to 9 units. We have 9 units of people. I can arrange these 9 units in can be arranged in 9 minus 1 factorial ways, which is equal to 8 factorial ways. But in this one unit consisting of 4 women, I can arrange themselves in 4 factorial ways. So this implies total is equal to 8 factorial times 4 factorial. Because I can arrange these 4 women among themselves in 4 factorial ways. Okay. Now let us answer the second one. So no 2 women come together. No 2 women come together means first we have to arrange men. So if you arrange men in a line 1, 2, 3, 4, 5, 6, 7, 8. If you arrange 8 men in a row, then we are going to get 9 gaps. But if you arrange these 8 men in a circle, we are going to get only 8 gaps. If you want, you can check it. The first man and the second man, we have 1 gap. And the third man, we have 2 gaps. Fourth man, we have 3 gaps. Fifth man, we have 4 gaps. Sixth man, we have 5 gaps. Seventh man and 8th man. So if you arrange these 8 people, 8 men around a circle, then we are going to get only 8 gaps. So in a linear permutation, we are going to get 9 gaps, but here we are going to get 8 gaps. This is the difference in a linear arrangement and a circular arrangement. Now, men can be arranged in men can be arranged in 7 factorial ways. In 7 factorial ways. Women can be arranged in 8p4 ways. So total is equal to 7 factorial times 8p4. So here you have to observe the difference. So if you arrange 8 people in a line, then we are going to get 9 gaps. But if you arrange 8 people around a circle, then we are going to get only 8 gaps. So if you want, you can check it using 3 people or 4 people, and then you can generalize. The next problem is like this. Find the number of ways of arranging 5 Indians, 4 Americans and 3 Russians at a round table. In how many of these all Indians come together? No 2 Russians come together. People of same nationality come together. So we have 3 questions. The first question is all Indians come together. The second question is no Russians come together. And the third question is all people of same nationality come together. Okay, so let us answer these questions one by one. So we have 5 Indians, 4 Americans and 3 Russians. So total 5 plus 4 plus 3, which is equal to 12. So we have 12 people. We have to make these 12 people to sit on a round table. So these 12 people can be arranged on a round table in 11 factorial ways. We can arrange them in 11 factorial ways. So this is the total number of arrangements when there are no restrictions. Now let us come to the first restriction. What is the first restriction? All Indians come together. So whenever you see coming together, we can tie up all Indians. So if you tie up all Indians, then we can treat all Indians as one unit, plus 4 Americans as 4 different units and 3 Russians as 3 different units. So 4 plus 3 is 7, 7 plus 1 is 8. So we have 8 units. This implies we have 8 units. Now these 8 units can be arranged in, so total arrangements is equal to 8 minus 1 factorial times 5 factorial. Since we have 8 units, these 8 units can be arranged around a table in 8 minus 1 factorial ways. After arranging these 8 minus 1 factorial, after arranging these 8 units in 8 minus 1 factorial ways, we can arrange 5 Indians among themselves in 5 factorial ways. Therefore, the total number of arrangements is equal to 8 minus 1 factorial times 5 factorial. Now the second question. So second question is no 2 Russians come together. No 2 Russians come together means first arrange Indians and Americans. So this we can do in 9 minus 1 factorial ways, is equal to 9 minus 1 factorial ways. Now first arrange Americans and Indians and Americans, and then Russians. So Indians and Americans can be arranged in 9 minus 1 factorial ways, which is 8 factorial. And after arranging these 9 people, we have 9 gaps. So these 9 gaps can be filled with these 3 Russians in 9p3 ways. So 9 times 9p3 ways. Therefore, the total number of arrangements is equal to 9 minus 1 factorial times 9p3, which is going to be 8 factorial times 8p3, 9p3. Now coming to the third one. All people of same nationality come together. So we can tie up Indians, Americans, can tie up Indians, Americans and Russians. So after tying up Indians, Americans and Russians, we can treat them as 3 units. Now the total number of arrangements is equal to 3 minus 1 factorial. These are the number of arrangements in number of ways in which we can arrange these 3 units, times 5 factorial times 4 factorial times 3 factorial. So these are the total number of arrangements in which all the people of same nationality come together. Next we have problems related to hanging models. The first problem is like this. Find the number of different chains that can be prepared using 7 different colored beads. I repeat, find the number of ways of preparing chains. Find the number of different chains that can be prepared using 7 different colored beads. So using these 7 different beads, we can form a chain in the sense we have to arrange these 7 beads in a circle. So number of different chains is equal to 7 minus 1 factorial upon 2. Since it is a hanging type, we have n minus 1 factorial upon 2. Both clockwise and anti-clockwise arrangement should be treated as a single arrangement. Therefore, the total number of arrangements is equal to half of the original arrangements. Okay. Now, let us look into the second one. Find the number of different garlands that can be prepared using 7 different roses and 4 different yellow roses, so that no 2 yellow roses come together. So we have to arrange 7 plus 4 roses. So here the condition is no 2 yellow roses come together. No 2 yellow roses come together means first arrange red roses and then yellow roses. So this can be done in red roses can be arranged in 7 minus 1 factorial ways. And after arranging these 7 red roses, we have 7 gaps. We have 7 gaps after arranging red roses. So number of ways of arranging these yellow roses is equal to 7p4. So total is equal to 7 minus 1 factorial, which is 6 factorial times 7p4. So these are the total number of different garlands that can be prepared using 7 different roses and 4 different yellow roses. 7 red colored roses and 4 yellow roses, so that no 2 yellow roses come together. So with this we have finished all the example problems before 5C. So now we have to look into problems in 5C. So all the problems in 5C are easy, so I am not going to explain all the problems. So here I am going to give only hints for few problems. Okay. The first problem is like this. Find the number of ways of arranging a chief minister and 10 cabinet ministers around a table, so that the chief minister wants to sit in a particular place. So we have a round table. On this round table we have to make these 11 people sit. Chief minister wants to sit in a special chair, so here we have this chief minister chair. So once we make the chief minister to sit here, we have to make the other cabinet minister to sit in this table, on this table. Now we have these 10 chairs. 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. So once we fix the position of a particular element, and then we can start numbering. In general, we cannot number the positions on a circle. So if we have 4 positions on a circle, I cannot say that this is the first position, this is the second one, this is the third one, and this is the fourth one. Once you fix some element, if I fix an element x here, then I can say that this is my first position, this is my second position, and this is my third position. So without fixing one element, I cannot say that I cannot start numbering the positions. So here what we can do is, here we are fixing the chief minister. I can fix the chief minister in only one way, because he wants to sit in the special chair. So after fixing this chief minister in this special chair, we have these 10 seats. Now I can make these 10 cabinet ministers to sit in these 10 chairs in 10 factorial ways. So let me write the hints. Chief minister can be seated in only one way. After that, we can number the chairs. Now the remaining people can be arranged in 10 factorial ways. So total is equal to 1 times 10 factorial. So some people will say that since we have 11 people, the number of ways of arranging these 11 people on a circle is equal to 11 minus 1 factorial, which is 10 factorial. But that is not the correct procedure. So here first we have to fix the constraint. The constraint is chief minister always wants to sit in a special chair. So for the time being, we assume that this is our special chair. So once we fix the position of chief minister, we can start numbering the seats. You can start numbering from here, or you can start numbering from here. No, I mean both the ways we will get the same thing. Okay. Our next problem is like this. Find the number of ways of arranging 7 guests and a host around a circle, if 2 particular guests wants to sit on either sides of the host. So let me explain the problem for you. So you have invited 7 people to your home, and you want to have lunch with these 7 people. Now out of these 7 people, 2 people are your special guests. Now you want to make those 2 people to sit beside you. So we have these 7 guests, G1, G2 and so on, G6, G7. and you are the host. Now these two special guests, G6 and G7, these two are your special guests. These two wants to sit on either sides of you. So this is your round table. So if you are sitting here, you want these special people G6 and G7 to sit here. Or else you can swap these two. You can have G6 on your left side and G7 on your right side. But these two wants to sit beside you. That means you three wants to sit together. You three wants to sit together, and in that sitting together, these two wants to sit on either sides of you. Okay, so total is equal to 8 people. But out of these 8 people, we can tie up G6, G7 and H. These are your special guests and you are the host. So now we have 6 units. I can arrange these 6 units in. We can arrange these 6 units in. We can arrange these 6 units in 6 minus 1 factorial ways. Now in this one unit which contains G6, G7 and H, I can arrange these 3 people among themselves only in 2 factorial ways. I can arrange them in like this: G6, H and G7, or else G7, H and G6. So we have only these 2 arrangements. Therefore total number of arrangements is equal to total is equal to 6 minus 1 factorial times 2. So these are the total number of arrangements. Now we have this special problem. You have seen this problem in linear permutations. Now we have the same problem in circular permutations. So you can clearly observe that the number of linear permutations and number of circular permutations are going to be different. Okay. In how many ways we can arrange 6 boys and 6 girls around a table? In how many of these arrangements all the girls sit together? No 2 girls sit together. Boys and girls sit together. So we have done the same kind of problem in linear permutations. Okay, so first let us write the information we have. We have 6 boys and we have 6 girls. So total we have 12 people. Now if there are no restrictions, then we can arrange these 12 people around a circle in 12 minus 1 factorial ways. Total is equal to 12 minus 1 factorial ways. Now let us answer the first question. So what is the first question? All the girls sit together. All the girls sit together means we have to tie up all the girls. Tie up all girls. So if you tie up all girls, then what you have is, you have 7 units of people. Now you can arrange these 7 units in. The simplest number of arrangements is equal to 7 minus 1 factorial times 6 factorial. Why we have this 7 minus 1 factorial means it is a circular arrangement. Therefore the number of arrangements is equal to n minus 1 factorial. Now in this one unit which contains 6 girls, we can arrange themselves in 6 factorial ways. Therefore the total number of arrangements is equal to 7 minus 1 factorial times 6 factorial, which is nothing but 6 factorial times 6 factorial. These are the total number of arrangements in which all the girls sit together. Now coming to the second one. No 2 girls sit together. No 2 girls sit together means first you have to arrange boys. arrange boys. So we have 6 boys, we can arrange these 6 boys in 5 factorial ways. B1, B2, B3, B4, B5 and B6. So we can arrange these 6 boys in 5 factorial ways. After arranging these 6 boys, we have first gap, second gap, third gap, fourth gap, fifth gap and sixth gap. After arranging these 6 boys, we have 6 gaps. So I can arrange these 6 girls in these 6 gaps in 6 factorial ways. Boys in 6 minus 1 factorial ways, which is equal to 5 factorial ways. After arranging boys, we have 6 gaps. So girls can be arranged in 6p6 ways, which is equal to 6 factorial. So total is equal to, so boys can be arranged in 5 factorial ways, girls can be arranged in 6 factorial ways. Therefore the total number of arrangements is equal to 5 factorial times 6 factorial. So these are the total number of arrangements in which no 2 girls come together. Now coming to the third one. So boys and girls sit alternatively. So if you observe, so in this position itself, boys and girls are sitting alternatively. Boys and girls are sitting alternatively. Therefore, the number of ways of arrangements in which no 2 boys, boys and girls sit alternatively is also the same. So I leave the third problem for you, because the third problem and second problem here in this circular permutations is going to be the same. So if it is a linear permutation, then it is going to be little bit different. So let me recall that linear permutation problem for you. Linear permutation. In that linear permutation, if you arrange 6 boys, 1, 2, 3, 4, 5, 6. If you arrange 6 boys, then we are going to get 7 gaps. But here in a circular permutation, we will have only 6 gaps. Now, if no 2 girls sit together, means I can arrange these girls in any of these 7 gaps. Okay. Boys and girls sit alternatively means if I arrange girl in the first position, I should not arrange in 7th position. But in this circular permutation, there is no question of 7th position. There are only 6 gaps. Therefore, the total number of arrangements in which no 2 girls sit together is same as the total number of arrangements in which boys and girls sit together, sit alternatively. Because the total number of boys is same as the total number of girls here. Anyway, I encourage the students to refer to that problem in linear permutations and get back to this problem once again. So here if there are 7 boys instead of 6 boys, then the answer is going to be little bit different. Next we have this problem. Find the number of ways of arranging 6 red roses and 3 yellow roses into a circular garland. In how many of these arrangements all the yellow roses come together, no 2 yellow roses come together. So this is pretty much similar to boys and girls. All the girls come together and no 2 girls come together. The only difference here is this is a hanging type, therefore we have to divide the answer by 2. So I leave the problem for you. And the next question is like this. A round table conference is to be attended by 3 Indians, 3 Chinese, and 3 Canadians, and 2 Americans. Find the number of ways of arranging these people at the table so that all the people of same nationality come together. We have seen a similar kind of problem in linear permutations. We have 5 mathematics books, 4 physics books, and 3 chemistry books. We have to arrange these books in a row such that all the books of the same subject come together. So here also all the people of the same nation should come together. So what you have to do is you have to tie up all the people of the same nation. So you can tie up all Indians, all Americans, all Canadians, and all people of the same nation, and then you can answer. Next we have this last problem. A chain of beads is to be prepared with 6 red colored beads and 3 different blue colored beads. In how many of these arrangements no 2 blue colored beads will come together? So first what you have to do is you have to arrange the red colored beads. Red colored beads can be arranged in 6 minus 1 factorial ways. So which is 5 factorial ways. After arranging these red colored beads, you can arrange the blue colored beads. You can arrange these blue colored beads in 6p4 ways. But since it is a hanging type, the total number of arrangements is going to be half of those things. So the total number of arrangements is going to be half of 6 minus 1 factorial times 6p3. So I encourage the students to write down the solutions of all the exercise problems. So with this we have completed the 5C. So in the next lecture we will deal with 5D, that is permutations with constraints.